right?
Yeah, Hamad bin Khalifa bin University.
Exactly. So bad in remembering names. Hamad bin Khalifa University. Exactly. So you're advised by Professor Marco August, right? He used to be, I'm not sure if somebody met him, he was a research scientist here at the WCC with Professor Markus Hardegger. Yeah, and today, hello. And today we have the honor to have you here as a visitor, and you will present your recent work, right?
Yes.
Title is Pano Style.
Yes.
Is there anything more to say? Because if not, I would like to hand over to you to watch your presentation.
Of course. Good day, everyone. I would like to introduce you to one of our recent work that we presented in ICCB together, that we attended recently. Also, I met Dr. Virsak Makel and Ahmed as well. I also met with Professor Peter Wanka there. So actually, this ground-breaking work that we presented there is part of a project called AIN2, which is shown in the slide. AIN2 is the artificial intelligence for indoor digital twins. We all know what is the digital twins because we are all working in the field of computer vision, and artificial intelligence also is well known to us. But the word indoor meaning we are concentrating on indoor environments instead of outdoor environments. So that is the brief introduction of the topic. And as you can see, there is something acronym WP3 as shown in the slide. WP3, it means since we are collaborating with other people from Qatar University and also from CRSPO. CRSPO is one of the research institute, I can call them, or something like that in Italy. And we are working together, so everybody has his particular package to work on. So we in Hamad bin Khalifa University, we're working specifically on visual representation, and I would like to take us through some preliminary results. It's already introduced. I'm working under the supervision of Dr. Marco August at Hamad bin Khalifa University, Qatar, which he was one time part of your BCC lab, BCC, right?
BCC.
The full meaning is Visual Computing, right?
Visual Computing Center.
Visual Computing Center. Yeah. He usually used to tell me that he really enjoyed when he was working here at KAUST. Yeah. So this project is sponsored by NPRP, Qatar National Research Fund, and this is me, Muhammad Tukur, PhD candidate, as already introduced under the supervision of Dr. Marco Agus at Idea Lab. Idea Lab is a lab that we are working also on data science and visualization stuff at Hamad bin Khalifa College of Science and Engineering. This is the summary of the work packages. First of all, we have the management and organization part, which almost everybody is participating. Yeah, all the collaborators, are participating in this package. So we have work package 2, which is about automatic reconstruction, mainly handled by our collaborator from Italy, CRSPO. Then with you, we have the visual representation generation, which is work package 3. This is handled by us at Hamad bin Khalifa University. Then we have work package 4, which is interactive exploration. This is particularly or mainly handled by Qatar University. Then we have the dissemination, communication, and exploitation. This is handled by GHD organization in Qatar. So this doesn't mean that we cannot collaborate and help each other in every package. We still work together to assist each other and publish some result together. Yeah. So, but as I explained before, we are mainly working on the visual representation generation, which involve the research and development activities aimed at creating editable visual representation for interactively transfer semantic and visual information between indoor scenes, and for establishing picture-based distance metrics among them and their components. Actually, our main work involves data pushing as well as point cloud, 3D representation, and style transfer. But it's good to mention here that as an input, we are targeting panoramic image as an input in order to generate the visual representation of the environments of the Indo that we are targeting. So panoramic image, I don't know whether we are aware of panoramic image. Since we are in the field of computer vision, I believe we are aware of what is panoramic image, which is a 360-degree image capturing very rich information of an environment. Yeah, so the main objectives of work package 3 that we are working on is we wanted to create data structures and models for accurate visual representation of Indo environments, feasible for interactive inspection and editing. If I say Indo environment, as I explained before, it means we are targeting something Indo as it is, meaning the living room, the kitchen, the toilets, etc. To extract and transfer visual pictures between panoramic images representing Indo structures. That is the second objective. While the third objectives, we wanted to see how we can define novel Indo similarity metrics for supporting editing, classification, and analysis of interior scenes. Before I take you further, the main application of our work is in construction industries. They said design as constructed as design, sorry. Also in real estate, whereby during the COVID era, it's very difficult. People are in lockdown. They found themselves inside house. They cannot go anywhere. So that kind of application can assist them to visualize the environment they want to buy or rent in a 3D manner without being physically there. Also, it can be applicable to interior designers as well, and other applications which might come later. So the work package 3 work description consists of 3 main tasks. The task 1 is about the Indo representation model. So wanted to have the Indo representation model in which we propose a spider, which is called spherical Indo depth renderer. It is a framework for processing, editing, and presenting immersive high-resolution spherical Indo scenes, which includes point cloud, 3D representation of Indo environments, content transfer, and immersive navigation and editing of clusters. While the second task is about data-driven style transfer. So in order to address these tasks, we propose what is called panel style. Panel style is nothing but semantic, geometry aware, and shading independent photorealistic style transfer for Indo panoramic scenes. Actually, this is our contribution that we presented in the PACE Computer Vision Aided Architectural Design workshop that took place recently in ICCB International Conference on Computer Vision in Paris. So these some of the problem we address in this particular work is about the issue of complex illumination patterns, issue of incorporating 3D characteristics in style transfer. Usually some traditional style transfer is all about the facial images, it's all about the perspective images, some generic images. But in this case, we are dealing with the panoramic image, which is a 360-degree image that requires a lot of work to do. Also, issue of equirectangular projection distortions are some of the issues we address in this particular work. Then the task is about Indo similarity. So this one is, we're yet to start to make any progress on it. So I don't want to talk much about it. So as for the task 1, in brief, which is about Indo representation model, as I said earlier, we present SPIDER, spherical Indo depth renderer. Spherical Indo depth renderer is an interactive processing, editing, and rendering system for Indo virtual reality applications. The method, as you can see, takes as input, use a single panoramic image as an input. So then captured using 360-degree camera. So then we have incorporated some deep learning models that allow us to extract the empty version of the given input, panoramic image. We also have some deep learning model that can assist us to have the semantic segmentation of a given model. We also have be able to generate the image, empty image depth, which is this particular image. We wanted to have the depth information for easy 3D representation as well as full image depth. So after extracting this information, also on top of that, we have the super resolution model where we benchmark the recent state of the art super resolution model and see which one can be much applicable, better suitable for panoramic images. So, you know, most of the virtual reality stuff or 3D representation stuff requires high resolution images. So therefore, for both the depth and the RGB panoramic images, we adopted the best state-of-the-art super resolution models in order to increase the details for better visualization. So then we have the viewer from this side where it can allow you to visualize the environment in 3D, as you can see in this video, allow you to visualize it in a 3D manner. And also we have some features where you can transfer content from the left scene to the right scene. So usually the left scene is the clothed one, while the right scene is the generated empty version. So you can see, for example, you can transfer the content. For example, this content, television can be transferred to the empty scene. As you can see, this window, some portion of it where some part of its component were taken from the left to the right. You can also insert objects. Some example will be shown very soon, and you can move the object from one place to another. So this is the first thing we have achieved regarding the task 1. For the task 2, which is the data-driven style transfer, actually, we can say that we propose the first semantic, geometry-aware and shading-independent style, photorealistic style transfer for indoor panoramics. And why we call it semantic aware? We call it semantic aware because the style transfer can allow you to transfer the content of the style of a particular portion of an environment. Not necessary to be transferring the whole environment. You can decide just to transfer the style of the, for example, office of that Birsak. You can just take the style of the wall and apply it to the, let's say there is the style is there in pink, here is white. You just take the style of his wall and apply it to the wall of this seminar room. You can also take the style of only the floor or the ceiling. So it's give you control to interact with the environment because it is semantic aware. We call it geometry aware because we maintain the 3D characteristics of indoor panoramic of the environments. We call it shading independent because applying the style on normal RGB images makes it to create bleeding artifacts. So due to that, we apply the style on top of albedo images instead of applying it on normal RGB. So this requires us to have apply what is called intrinsic image decomposition in order to extract the shading and reflectance. And the remaining of the explanation will come in the coming slides. This is the paper that is already published in ICCB recently. For more details, you can go to the reference. So as I said, the application of style transfer to indoor panoramic scenes generates have like a lot of several significant challenges, which are not limited to complex elimination patterns. Consider in this environment, the light in some portion of the room is less compared to the other part of the room, right? So this is some of the issue we address, incorporating 3D characteristics, EQ rectangular projection distortions, and high resolution requirements by adding on top of that the super resolution model. Therefore, our proposed approach addresses all these challenges, and on top of that, our architecture is able to generate photorealistic indoor panoramic scene in a controlled fashion, as I mentioned, as it is semantic aware, so you can decide to apply the style from one portion of room to another portion of room, not necessary to be whole. So our architecture also, on top of that, some technical contributions, as mentioned, is the shading independent style encoding, unlike the traditional ones, and geometry aware discrimination. What do I mean with the shading independent style encoding? Actually, we propose to model the illumination of an indoor scene according to intrinsic image decomposition. What is intrinsic image decomposition? Intrinsic image decomposition is a well-known and challenging problem in computer vision, which has diverse applications. For example, it is used for material object recognition, image editing, and scene understanding. And the goal of intrinsic image decomposition is nothing but to distinct the image component, for example, the shading, the reflectance, and illumination, so that they can be analyzed or manipulated independently. And we approximate the shading as a normalized neutral modulation signal using the Gibber relationship. And this particular portion of the methodology or the framework summarize the whole explanation. So we make what is geometry aware. This is one of the novelty incorporated. So the thing is, we impose the scene depth, the layout, and edge consistency with additional geometry losses. For example, for the depth, we incorporated we utilized the slice net. For the layout prediction, we utilize the horizon net in order to impose the geometric and latent consistency of layout of the generated scene. As for the edges, we use the Sobel to impose the geometric consistency of the edges of the generated scene. And for the equirectangular projection distortions, we compensate that through area-based weighing, while for the, and also we exploit the latent features extracted during the depth and layout predictions for driving geometry losses, imposing global and local similarity. So this is our quantitative result, where we show clearly from the top, we are comparing our work with the state of the art, which is the shown and the danced. Shown is the semantic aware style transfer, while dance is the depth aware. So it's like we're taking each ingredient from each one and trying to make it work in one model. So we make our own to be semantic aware and at the same time depth aware. Not only depth aware, but also other geometry losses like edge, like layout as well. So that is why we have a better advantage. And on top of that, we make our own to be shading independent so that to avoid the lighting artifact, bleeding artifacts. So with that, we were able to achieve 6.95 higher fake signal to noise ratio percentage. And also we are able to achieve 25.23% higher structural similarity, and also a 26.76% lower at FID, which is one of the metrics for measuring the distance. So from the top, from the bottom, we are doing like a ablation study to see if we remove each component that we incorporate in the system, how it will look like. So quantitatively, you can see clearly that when we remove the layout consistency constraint, so we are generating less results compared to the complete package. Also, when we remove the depth, and also we remove the geometry. But as you can see, the most important fact is the shading decomposition, intrinsic image decomposition. So because when you remove the shading feature, you see you are achieving very less compared to the rest. So this is part of the results in the video, but I would like to show you that in the coming slides. So here, just to give you the hints that in order to come off about which geometry loss to use, so we do like a kind of investigation to find out the performance of various geometry losses in the context of structured 3D dataset. So we do weighted, we try the weighted MSC loss, the Beru loss, weighted Beru loss, and the MSC and Sobel loss. And we end off utilizing and adopting the weighted MSC loss because it's generate better results. And also we try to compare our generated reconstructed images compare with the ground truths This is very important because in style transfer, you want to make sure that the preservation of the original image structure is very important. So I want to make sure that whether we are maintaining the structure of the original image. So we do comparison where we compare the original ground truth basis, our reconstructed image, where we present the result here. As you can see, we are achieving 92%, which is very close to the original, and we are also achieving the lower RFID of up to 4.2. So this is about this. And this is part of the qualitative result. So as you can see, these are the style images, and these are the content images. So when you apply this style image to this content image, this is the result. As you can see, did you notice any difference between this one and this one? Of course, there is difference, right? So you can see it is the same environment, but the world has changed by taking the style of the style image. And also, as you can see, the door is in this brown or something like that. But here it's picked the color of the door of the style image where it changed to white. So you can also see the flow has changed. So the most clear example is this one, where you can see clearly that the wall has changed completely from this color to pink. So also you can see here, we decide, this example particularly, we decide even not to change the cabinet style. So just to show that the semantic awareness is working. So we try to show that you can decide not to apply the style to a particular portion of the image. So the rest are also the same thing as I explained in the other rows. So this in particular is just to show you that also our system supports style crossover, where you can apply more than one style image to one content image. What do I mean with that? I mean that, for example, this is the different room, and this is another different room, different indoor environment. So we took the style of the wall and the door from this image and apply it to this, and we are generating this one, right? But still, we are taking, at the same time, we're taking the style of the floor and the ceiling from style 2 and applying it to the same image to generate the same image with different ceiling and different floor. So you can do not only restricted to only 2 style images, but also to many style images, depending on the number of components and depending on how much control you wanted to apply. And here we do like a kind of quantitative, qualitative result comparison using the Euclidean image difference between the ground truth and generated stylized images. So you can see, even though ours also is not 100% out of artifact, free from artifact, but at least, as you can see, the bluer the better, the greener means the more artifacts. So we have shown that from the ground truth, we took some details. For example, here we took only the portion of the window, and here we took some what do you call it? A kind of art, right? Also here we took like a portion of also another window, just to show that the difference between our results and other state-of-the-art shown under depth-aware neural style transfer. It is clearly that our result is less artifact compared with the other state-of-the-art. So the next slide is also more results or qualitative results. We're using self-style transfer. Self-style transfer means we're applying this image, the content image and the style image is the same. So just to do for a pair comparison. So we make why we do that, because one of our competitor, which is the danced, is not semantic aware. So to be fair to it, so we do like a self-style transfer comparison, where we apply the same content as style image to, so the same content image is the same as the style image. So this is the label, which is the semantic information, and these are the ground truths. And this is the result generated by Dunst, and this is the result generated by Sean, and this is our result. So it is clearly the judgment is yours. Yeah, so also here, we do the same, but using external image style transfer to show not only the semantic awareness, but also the depth awareness and the sharing independent, how important it is. So this is our result. Sorry, this is the content image, this is the style image, and this is the result generated using Sean, and this is the result generated using ours. So also here we do a kind of qualitative ablation study in which we remove, for example, here we remove all the geometry constraints that we incorporated in our approach and see how the result will be. So it is clearly that the result generated without the geometry constraint is less qualitative, less visually appealing than the result with the complete package. So here, which is almost at the last part of the presentation, is the video summarizing the whole qualitative results, because you can also visualize the same results using the panel style, using spider spherical indoor depth renderer. So this is the original scene, and this is the scene generated by Dunst, which is one of our competitors. And this is the original, and this is panel style. So it continues like that for different kind of scene. So just to show the differences between the result generated by our model and the one generated by state of the art. So it is up to you to see that, to do the judgment, right? Which one is generating the better qualitative results. So this is at this point. Also, this is the comparison with the state of the art using self-style assessment. As I already explained, self-style transfer means applying the content, and the content image and the style image is the same. So this is the result generated. This is the original. This is the final style without the geometry, while this is our approach with all the complete package. Also at the same time, by the left side, we are showing the original image. So this is at this point, we have the last part, which is the one for the external style transfer, which I think after this thing it will come. Okay, so this is the last portion, application of different style to some target image, as already shown in the almost 2D example, right? But this one is visualized in a 3D manner. So this is original, this is stylized, this is original, this is stylized, and all are generated using our approach. So what is the next now? The next is, this is some part of the publications from our work, which we already published in ICCB, as well as the in graphical models, CBIA, and also some are under review. And so what's next? So these are some of the limitations. We wanted to have the network for extracting multiple signals from the same image. Why we need this is because all these were achieved because we have the dataset. The dataset is already provided from structured 3D dataset, which is the synthetic dataset. So when we wanted to have it in a real environment, so we need to have a model, a network that can assist us, support us to generate all the required signals, such as the albedo, the shading, the semantic segmentation, as well as the other input, which is the which one did I mention? I think I didn't mention the reflectors, right? So all the signals required, the depth information as well. So for the real image, so that when you give us only one particular panoramic image, we can generate the 3D representation of it with all these kind of features. So we also wanted to have more accurate shading models, issue of integration and deployment that can be utilized even in our mobile phones. We wanted to also create more immersive visual staging applications. And I think for generalization to the world, we already started doing something, but the main challenge now is about having the semantic segmentation, which even during the ICCB, I see a lot of people working on that particular challenge. So I think that is all for now. Thank you for your listening.
Thank you very much. Right. Any questions from the audience? Comments? If not, then maybe I will start with a question.
Yes.
About all your implementations. Is this open source? Is the code available?
Yeah, I think we are yet to make it public, but we are working on that.
Okay. Okay.
Yeah.
Can you also shortly elaborate about I don't know, training times and stuff like
yeah,
this?
This is provided in our paper, which already published recently. So actually, it requires like to train the images. It requires it depends on the GPU you have. Actually, we have some challenges initially because we were using very low GPU. It was the 12 gig, but later we were able to have like a 50 gig. So still to train the model, it requires us to spend like 8 hours, 8 hours to 8 to 10 hours.
Just that when we are here at KAUST, can you explain how it is in Qatar? What's the infrastructure, the computing infrastructure that you have and you use? Is there also like some GPU cluster? What do you guys usually use?
Yeah, we do have the GPU, for example, like each and every PhD student that is he's doing computer vision, data visualization, research. So he will be allocated with some GPU resources. But mostly people are getting like 10 gig GPU, 20 gig GPU.
Okay, but this is one GPU and this is assigned to you just in one machine?
The one assigned to me is 10 gig, but when I requested for the higher GPU, I was given access to virtually, not actually, virtually to 50 gig. And also we have the QCRI, Qatar Computer Research Institute, where they have also higher GPU, but that one.
Which architecture do you know, like V100s, A100s? What do you guys usually have? Can you tell?
Again?
A100s or V100s and the NVIDIA GPUs, what kind?
We are using NVIDIA 1080, I think.
1080?
Yeah.
Okay.
What?
Okay. It is just that 1080 is rather weak in comparison to like V100s, A100s.
I see. I think we can see that directly from the report, what we reported in the recent published Fano style paper. So we already mentioned, let me go directly.
Just should keep the time in mind to get a table, because honestly I forgot to reserve a table in the diner.
I see. So just to be to give you a specific answer, I think I would like to take us to the description of the resources we use. So we're using this NVIDIA Quadro RTX 800 equipped with 48 gigabyte GPU. Yes, so this is the details of the.
Okay.
Yeah.
I see. Okay.
Yeah, I'm not that expert in knowing the different classification
no problem.
GPUs.
Just curious.
So maybe I can. The follow-up question to you here is that which one you are utilizing here?
I mean, we have our IBEX cluster.
I see.
And we have plenty of V100s, A100s.
Yeah.
And I think first quarter, so next year,
I see.
Shaheen 3 will come out, new supercomputer.
Yeah.
And this will have, does somebody have the numbers in mind? How many H100s? If we get them, how many? 2000. So like, yeah, 8,100. So the very new NVIDIA GPUs.
I see. You mean 2000 GPU?
Yes.
Gig.
Numbers.
Numbers.
Each with numbers. And
I see.
each with 80 euros. A little more. I cannot.
That is very rich.
Yeah, I mean, this thing costs what? $80 million?
Yeah, of course. By the way, before I started my journey to go to the Paris, I was in discussion with my professor, Dr. Marco.
Mm-hmm.
He told me that also there are some GPUs that are on the way to arrive.
Okay.
Even though I didn't, I'm not careful about the specification, but we're hoping that we're also getting better GPUs.
I see.
But still, I don't think it's up to this number that you're mentioning.
I mean, this thing, even this Shaheen 3 that's will come next year. I mean, this is crazy.
I see. I think that is nice.
Yeah. All right. Any more questions, comments? Because if not, I would like to thank you again for coming to KAUST, visiting us, giving a very nice presentation. Thank you very much to see what you guys are working on. All right.
Thank you all.
All right. Thank you very much. Thank you. All right. Who did not get yet a meat badge?
We have, I think that Jans, I don't know, he is online. Maybe he has something to say. That Jans, are you with us?
Hi. Yes, I'm with you. Hi. I joined late. I just saw your message. Hi. So let me also open the camera. Hi.
Hello.
So yeah, to be quite frank, our GPU resources are nothing compared to KAUST, but we'll try to make do with what we have, as you saw. And the issue is we are configured very differently from you. So I caught your question earlier. So we are configured very differently from you because we have a lot of students who request a sandbox, and then we dedicate a GPU to them. We are not at scale to run any Slurm, any Jupyter Hub.
Exactly, that's what we have installed on our classes. Exactly.
I'm fully aware of your systems because I know people at KAUST as well, and we are not yet there. We are still ramping up. Whenever there's leftover budget, we put in more GPUs, and that is where we are.
Okay, I see. All right. Sounds good.
So some of you are, you know that Jans, he was with you also here.
Also here. Yes, exactly. We met actually in 2018. I've been here for a week. I was in your office. You explained one paper to me that I could have made a talk about it afterwards.
We did meet, yes. How was life at KAUST?
So far, so good. Currently, pretty hot.
Here too.
Yeah, this I can imagine. So, no, but life is good. Yes.
Yeah.
Awesome.
All right. Perfect. Good. Nice to see you, Jens.
Nice to see you too.
We will go for lunch. Otherwise, I think we will not get a table.
Okay. Thank you for joining. Thank you for your contribution, sir.
Thank you.
All right. Have a great stay.
Thank you.
Right, so I have plenty. Please one. You didn't. Oh my God.